Hello, my name is Christian Figueroa, and I'll be doing extra credit for PS1. So I'm going to do 1 through 10 real quick. So for question 1, it says to list all the elements of the following sets, and then we're given 5 different sets we're supposed to list the elements of. So reading set notation for set A, we have 1 over n, and then n is going to be the numbers 3, 4, 5, and 6. Okay, since we're giving 1 over n, which means we're going to plug in the numbers for n throughout the set for the elements. So if you plug in with all the elements that we have, 3, 4, 5, and 6, then we get 1 over 3, 1 over 4, 1 over 5, and 1 over 6. Moving on to the set B, we have A is going to be the elements in the alphabet, and then A precedes F. And I've written up here that in like a notation where we have the bounds of equal to A but not equal to F, all the way going to F but not equal to F. So it means from A all the way to E really. So the letters in the alphabet are going to be A, B, C, D, and E. For set C, we have x is going to be an integer and then x is equal to x plus 1, knowing that we can't do x is equal to x plus 1 because that just wouldn't make sense at all mathematically. We have a null set or nothing in it. Then we move on to D. So the set is n squared, where n is -2, -1, 0, 1, and 2. Simple enough. We just plug in n and the n squared, and then we get our answers. So the elements are going to be for -2 squared is 4, -1 squared is 1, 0 is 0, 1 squared is 1, and then 2 squared is 4. Now, for the actual elements itself, we don't have to repeat them at all. Since we have duplicates of 4 and 1, so we just write 0, 1, 4 in ascending order. The last one would be E, where n is going to be basically a factor of 24. So here, I just broke down the left side 24 into its factors. So 1 and 24, 2 and 12, 3 and 8, 4 and 6. And you're just going to list them all out. So 1, 2, 3, 4, 6, 8, 12, 24 is going to be all in the set. Moving on to set B, now we're moving away from having to solve for the elements, and now we're actually solving for the notation itself. So if you look at the elements in set A, it's 1, 2, 3, 4, 5, 6, 7. We can see that it goes from 1 to 7. So we can say that x is going to be all the numbers from 1 to 7. So x is going to be p, and then we have from 1 is greater or equal to or less than or equal to x, which is x is less than or equal to 7. Moving on to B, this one's a little bit trickier. You can see that it increases by a factor of 10 every single time. So we have 1, 10, 100, 1,000, and 10,000. So, and then I just counted how many times we multiplied by 10. So 1, 2, 3, 4. So we have a number x. X is going to be equal to 10 to the power of n. And then n is going to be a positive integer. And then the n is going to range from being greater than 0 but less than 4, or greater than or equal to 0 but less than or equal to 4. So from 0, 1, 2, 3, 4, so we plug in, we can just test right real quick. X is equal to 10 to the power of 0, we get 1. X is equal to 10 to the power of 1, we get 10. X is equal to the power of 10, or is equal to 10 to the power of 2, 100. You can see how the pattern goes all the way up to 4. C, we have a set of elements that go 1 to 1 over 2 to 1 over 3 to 1 over 4 to 1 over 5 to ... which means it goes on infinitely. So I wrote down underneath, we have actually 1 we can rewrite as 1 over 1, and then 1 over 2, so it's going to be the same, 1 over 3 or 4. And I said, basically, I can recognize that this pattern is 1 over n. So I said that we have 1 over n in the beginning. That's going to be our condition. And then n has to be an integer that is positive, because if it was negative, then it would not exist at all. Sorry, my mistake. We know that it goes from, the n goes from 1 to infinity, but it goes positively. So we say that it's an integer that's positive. For D, we have 0. This is simple enough. We have a one element set. We can say that x is just equal to 0, and that's our answer. For 3, we're given 3 sets, A, B, and C, and we're determined which are true. And then we're supposed to give reasons for those answers. So for 3, we have 3a, we have 3 is an element in A. If we write out the elements in A, 0, 2, 3, this is true because 3 is an element of the set A. Moving on to B, we have the set 3 is an element of A. Now this is different because it's in set notation and not just the element itself. We don't have an element with the brackets like for 3 here. So we say that it's false and then set 3 is not an element of A. For C, we see that we have a different notation, which is like a C with a line underneath it. This just basically means that 3 is a set, and that 3 set is a part of A, which is not true. Basically the same thing as the last answer. It's false because 3 is an element, not a set. It's false. Moving on to D, we have the same notation as last time, where B is a subset of A. If you look at the elements of B, we have 2 and 3. If you look at the elements of A, we have 0, 2, and 3. All elements of B, 2, and 3 are in set A, 0, 2, 3, which is true, which you can say all elements of B are in A. Now, if we flip it and say that A is a subset of B, this would not be the case. First off, there are more elements in set A than there are in B, which would make it not a subset of B. Plus, there is not a 0 in B. So we say A is not a subset of B, and this entire question for E is false. Move on to F. That notation with the circle and the line slash through it, that is actually a null set, which means there's nothing in it. It's technically true that nothing is in C at the same time, so we can say that null set can be a subset of any set. It could even fit into A and B, so it is true. Going on to G, we can see that again, it is asking, or it's saying that a null set is an element of A. We don't have a null set listed for A because it is not an element in A, so we can say it's false. Moving on to H, we have notation that A is a subset of A. This is basically just like a one-to-one type of thing. 1 is equal to 1. A is equal to A all the times. All elements of A are in A, so it's true. Moving on to 4, it's asking us to define basically set notations with A and B, C, and the universal set. So the first one is A upside down U and B. This is actually an intersect. So it's basically asking for what elements in set A and B are the same. So A is 0, 2, 3, just like the last problem. B is 2, 3, just like the last problem. You're asking what are they sharing? They share the elements 2 and 3, so 2 and 3 is our answer. For B, it's a U, which means union, which means all the elements in both A and B combined. A is 0, 2, 3. B is 2 and 3. It's just basically set A, 0, 2, 3. B or C, it's asking for the same thing. It doesn't matter if they're reversed for a union or intersect, so we get the same answer as C or as B. For D, we're asking for all the elements in A and C. This one's going to be different from B because set C has different elements. So for D, we have 0, 1, 2, 5, and 9. For E, A minus B, which is completely different from algebra. This is basically asking for all the elements in A that are not in B. So if you took a set A, it's 0, 2, and 3, and set B is 2 and 3, we can see that 0 is not in B, but it's in A, so our answer is going to be 0. For F, it's asking for the flipped version of this. Now remember that set B is a subset of A, which means all of its elements are in A, which means that this can't be true at all. There are no elements in B that are not in A, so we say it's null. For G, it's asking for all in the universal set, which is ranging from 0 to 9, but that's not an A. So A has 0, 2, and 3. The universal set has everything. So basically we're saying what is not in A that's in a universal set. So it's 1, 4, 5, 6, 7, 8, and 9. For H, it's asking for the same thing, but for set C, it's a different set of numbers. We have 1, 5, 9 compared to universal set. So you just list all the numbers in the universal set that's not 1, 5, 9. So 0, 2, 3, 4, 6, 7, and 8. For I, we're asking for the intersect between A and C. You can see that there are no intersecting elements in either set, so we say they have nothing in common. It's a null set. For J, this is a little bit of a different notation. It's a circle with a plus sign in it. Um, it's basically just asking for everything that's in A and B, but not in both. It's like an intersect with extra steps. So we can see that they both have 2 and 3, so we can't list those. But A has 0 and B doesn't have 0. So we have all the elements that aren't in both. It's gonna be 0. 5. We're just basically given a universal set, and we have to illustrate different conditions to see that they're true or not. For if A is a subset of B, which means if all elements of A are in B, and all elements of B are in C, then that means that all elements of A are in C. It's like it's like a chain rule type of thing. So I made up the really simple set of different type of sets. A is equal to 1, B is equal to 1 and 2, and then C is equal to 1, 2, and 3. So you can see on the right side, A is a subset of B. That is true because element 1 from A is in B. B is a subset of C. That is true again because elements 1 and 2 are in C. And we can see that element or A is a subset of C as well because element 1 is in C. For B, there are sets A and B such that A minus B does not equal to B minus A. So if you go back to the last problem, we can see that these were not the same. So we're looking to prove that again, basically. So given a set A, 2, 3, 5, and 8, and a set B, 2, 5, 7, and 9, if we did A minus B, we get that there's a set 3 and 8. And if you did B minus A, then there's a set 7 and 9. Remember, A minus B, everything in A not in B, and then B minus A, everything in B not in A. So we set them equal to each other, and we see that that's not true. So we prove basically that B is true. For C, if the universal set is equal to a union between A and B, so if the universal set is equal to everything in A and B combined, and the intersection of A and B is not true, where there's nothing in common, then that follows that A is equal to the universal set, everything in the universal set not in B. So given we have a restriction where A and B have to have all the numbers in a universal set, but at the same time, they can't share any numbers between themselves. So I did even and odd. A is equal to 1, 3, 5, 7, and 9. B is equal to 2, 4, 6, and 8. Moving on, we see that the union between both of them, A and B, is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. The union set, which is true. Now we're looking at the intersection. We can see that there's nothing intersecting between them because one is odd, one is even. So that's true. Now, A is equal to the universal set minus B, knowing that the universal set has all numbers 1 to 9, and B is only even numbers, that means that U minus V would be the remaining odd numbers. So 1, 3, 5, 7, and 9, which is true. I'm going to stop it here, and then we're going to move on to 6 to 10 in the next portion.